you'll be happy to know that this section on linear approximations and differentials is far more straightforward than the section on related rates. The homework problem should take a lot less time, and so will this video. We've been using the differentials, dx and dy, for some time now, but we've never actually formally defined what is dx and what is dy. In this section, we do that. In addition, we're going to note that we can use the tangent line to approximate a function, provided that it is differentiable on an interval about the point where we want to find the value of the function. Now, why does this work? Why is the tangent line a good approximation to the function close to the point where we want that function value? Well, as long as the function is differentiable about that point at that point and defined around it, then the graphs should be close together. When you zoom in on the graph at the particular point where you evaluated the derivative, you'll notice that that section of the function is more and more linear the more you zoom in. This is called local linearity. In this section, we'll just use the tangent line to approximate function values close to the point in question. However, we can extend this idea in calculus too to higher degree polynomials that will be used to approximate other types of functions, such as sine of x, e to the x, or natural log of x. Let's take a look now at the learning objectives. In this section, we're going to describe the linear approximation to a function at a point. The linear approximation is the tangent line. Write the linearization of a given function, which means we write the tangent line. Draw a graph that illustrates the use of differentials to approximate the change in a quantity. This is where we define the difference between dx and dy and dy and dx. Then we're going to use the definitions for relative error and percentage error in using the differential to approximate a value on a function. Let me share my screen so we can get started. So we now want to define more formally what the linear approximation to a function at a particular point is. It really is just the tangent line. Let's consider a function f that is differentiable at point A, meaning that the function has to be defined there and continuous there, and the derivative is defined there. Remember that the tangent line at that particular point can be given by this equation here, y equal to f of a plus f prime of a times x minus a. In fact, this equation is just the point slope form of a line in disguise, where you have y minus y1 equal to the slope times x minus x1. y1 is the function value at a, which has been moved to the right side of the equation. Again, the slope is given by the derivative at a, which is the slope of the tangent line. Now, this formula implies, of course, that the derivative has to exist because we're using the derivative in the formula. Provided that it is going to be differentiable, the tangent line will be close to the function at that point. Let's look at the graph of 1 over x in quadrant 1. You can see the graph here in the orange-red color. The tangent line at x equal 2 is graphed in blue. You can tell that the tangent line has a negative slope because it is decreasing left to right. There's a rectangle around the point where the tangent line and the function meet at x equal 2. We want to blow up this section of the graph, which is what you see here on the right. When we zoom in, notice how close the tangent line in red is to the graph of the function. Oops, I got it backward. The function in red compared to the tangent line in blue. They're very close together. Instead of taking a value that's on the actual function, I could approximate it with a value that's on the tangent line. The closer I get to 2, the better the approximation will be. Also notice how linear this section of the function appears. We know the function's not linear from looking at the graph on the left, but when we zoom in on a particular point, it becomes more and more linear if it's differentiable in that interval. We're going to define the linear function L of x to be this tangent line equation, f of a plus f prime of a times x minus a. This is called either the linear approximation of the function or the tangent line approximation. It's also known as the linearization of f at x equal a. In other words, you're approximating what may not be a curved function with the linear function, which is the tangent line. These linear approximations are very useful for approximating roots and logarithms. Yes, you can approximate them without a calculator using a linear approximation. Let's see how accurate this would be by looking at some examples. In example 1, we want to find the local linear approximation to the function the cube root of x at the point x equal 8. 8 becomes our value of a. Now we know what the value of the function is at 8. The cube root of 8 is 2. But what if I wanted to know what the cube root of 8.1 was, or the cube root of 7.8? Those values are close to 8, but they're not 8. I would need a calculator to be able to find those, except that now I can use the local linear approximation. In other words, the tangent line to the function at the point 8. So now let's go ahead and use this equation to estimate the value of the cube root of 8.1 to 5 decimal places. I'm going to use a as 8. This means that L of x is equal to the function value at 8 plus the derivative evaluated at 8 times the x value minus 8. What is the function value at 8? Well, we said the cube root of 8 is equal to 2. That will replace this first term. What about the derivative at 8? To find the derivative, let's take the derivative of the function. The derivative, f prime of x, means to take the derivative of the cube root, but it's hard to take it in that format. So instead, we rewrite the derivative as the 1/3 power. Then we can apply the power rule, bring the 1/3 to the front, subtract 1 from 1/3 to get negative 2/3. This is the same as 1/3 times the cube root of x squared. Let's now compute what the derivative is when x equals 8. This means that I have f prime of 8, which comes out to be 1/3, the cube root of 8, which I know is 2, squared. This becomes 1/3 times 2 squared, which gives me 1/12. I can replace this now with 1/12, and I have an equation for the linear approximation function. In other words, the tangent line at x equal 8. Now I want to use this to approximate the cube root of 8.1. So I'm going to let x be 8.1. this is going to give me 2 plus 1/12 times the difference between the two x coordinates is 0.1. 0.1 can be written as 1/10, which gives me 2 plus 1 over 120. When you get a common denominator and work it out, you end up with approximately 2.0083 repeating. Now, what does that tell us? Well, it tells us approximately what the cube root of 8.1 is. Grab your calculator now and compute what the cube root of 8.1 is on your calculator. Let's see if I can find it. The cube root of 8.1 on my calculator comes out to be 2.00829,885, and it keeps going. In other words, it's accurate to 3 decimal places. And if you round to 4 decimal places, this is tremendously accurate. It's accurate to the 1,000th decimal place. And if you round to the 10,000th decimal place, this gives you a way to compute it without needing a calculator. Let's take a look at another example. We're going to take a look now at example 2. In example 2, we want to find the linear approximation for f of x equal to cosine of x at x equal pi over 2. This means that while we're going to use the tangent line at pi over 2, we're interested in points very close to pi over 2, but not exactly pi over 2. For example, it might be 85 degrees or 98 degrees, something close to 90 degrees, but not 90 degrees. Let's go ahead and find the linear approximation function for this now. In order to do that, we have to identify our a as pi over 2. Then we have to compute the function value at that point, which will give us cosine of pi over 2, which we know is 0. Then we need the derivative for the slope of the tangent line, and the derivative of cosine of x is negative sine of x. Then we evaluate the derivative at the value of a. This gives me negative the sine of pi divided by 2. And this comes out to be negative 1. I'm now ready to write the linear approximation function. L of x is equal to, where'd it go? 0 minus 1 times x minus pi over 2. Or in other words, negative x plus pi over 2. I could use this to find something that is between, say, pi over 3 and pi over 2. Any kind of angle that's in that range, it ought to be relatively close. The closer I get to pi over 2, the better the approximation is going to be. We can also use the linear approximation to estimate values that are raised to higher powers. Yes, we could multiply it out 4 times, but that's a lot of work. In this case, we want to approximate the function 1 plus x, quantity raised to the 4th power, near x equals 0. We're going to use this to approximate the value of 1.01 raised to the 4th power. In this case, our a is equal to 0. Then we're going to write f of a, which is f of 0, which becomes 1 plus 0 to the 4th, which is just 1. Next, we use the power rule and chain rule to find the derivative of the function. 4 times the binomial to the 3rd times the derivative of the inside. The derivative of the inside is just 1. So we end up with 4 times the binomial to the third power. When we substitute 0 in place of this, we end up with 4. Now we're ready to write the equation of the linear approximation. When we write the equation of the linear approximation, we're going to be substituting in the values of the function at a and the value of the derivative at a. The tangent line approximation becomes 1 plus 4 times x minus 0, which simplifies to 1 plus 4x. Now we want to use this to approximate the power 1.01 to the fourth power. Now, when we do this, we have to think about what the value of x actually is. What we want to raise the power is 1.01, but the thing being raised to the power is the binomial 1 plus x. What would x need to be so that 1 plus x is 1.01? You're right, x needs to be 0.01, not 1.01. We need this to be true. Now we can find L of 0.01 using the formula and realizing that 0.01 is 1/100th. We can end up with 1 plus 1 over 25, which turns out to be 26/25. This comes out to be 1.04. Take your calculator and raise 1.01 to the fourth power now. On the calculator, we get the following value. We end up with 1.01 to the fourth power of 1.04060401. Again, it's accurate out to 3 decimal places. This is a tremendous amount of accuracy and will suffice in many, many cases. And it's relatively simple mathematics. It's now time to talk about what the differentials are. We've been using dx and dy quite often in this course, but we've never formally defined what dx and dy are. We need to do that now. These linear approximations are actually where the dx and the dy come from. They correspond to a small change in x or a small change in y on the linear approximation function. This gives us a way of estimating the function changes as an effect of a small change in the input values. These correspond to Leibniz's notation of dy and dx. Let's now look at the connection between differentials and the linear approximation function. When we think about the linear approximation function and we think about the actual function, we want to know if a small change in x occurs, what's the change in the y value? On the actual function, if we change our x value from a to a plus delta x, where delta x is a small amount, something like 0.01, then the change in y is given by delta y equal function value at a plus delta x minus the function value at a. In other words, to find the change in y, subtract the 2 y values. Notice that on the actual function, we're using delta x and delta y, not the differentials dx and dy. This is the true actual change in the y value on the function. Instead of calculating the exact change, delta y, though, we can approximate it with the tangent line approximation, the linear approximation function. Let's look at the changes on the linear approximation function. In other words, the tangent line. If I want to look at those, the change in the y value, or the change in L, is what we define to be the differential dy. In other words, that differential dy you've been using is actually the change in y values on the tangent line approximation. And it's given by L of a plus dx minus L of a, change in the y values on the tangent line, given a small change in the x values. Notice that we use dx again on the linear approximation function. We want to figure out what the relationship between dx and delta x is. Dx on the tangent line, delta x on the function, and dy and delta y. Dy on the tangent line, delta y on the function. Using the definition of the linear approximation function, we can write that the change in y values on the tangent line is given by L of a plus dx minus L of a. But we have the definition for L. Remember that the definition for L of x is equal to f of a plus f prime at a times x minus a. We take these values, a plus dx and a, and substitute them into the definition of the tangent line approximation. Notice that in the first one, this gives us an a plus dx minus a, and the a's cancel to give us a dx. In the second one, notice that we end up with a minus a, which gives us 0. So the second term drops out, and we get minus f of a. But the first one had a positive f of a, so the f of a's drop out. And we can see that the change in y values on the linear approximation function, this of course being dy, becomes the derivative at a times the differential dx. Dy equals f prime of a dx. And you know already, you can tell if you abuse the notation and treated it like they were, well, numbers, and divided both sides by dx, you would get the derivative notation, dy dx. This is called an abuse of notation because they're not. They're actually operations. Let's now take a look at a picture where we can represent these different values. The true function is here in blue, and the tangent line approximation at the point a, f of a, is in orange. We can tell that as long as we're close to a, the tangent line is very close to the function, and the function is nearly linear close to a. Now what we want to do is look at these 2 points here. The lower one is on the tangent line, and the value here has to be a plus dx, the small change in x, and the y value is the linear approximation at a plus dx. This dx corresponds to the distance between a, f of a, and that point. Now let's look at the upper point on the actual function. This is on the actual function. Notice that it really should be a plus delta x and f of a plus delta x. However, they wrote dx. Why did they do that? Notice that dx and delta x are the same. That's right, the differential dx is actually the change in the function as well. So dx and delta x are identical. They're equal. It is not true for dy and delta y. Let's look at delta y. Delta y is on the actual function. It's the change in the y value between the upper ball here down to the height of the lower one. This is our delta y. You can see it's written out to the side here. That's the difference in the y values between the 2 points on the blue curve. Let's now work on the tangent line. We again have 2 points on the tangent line, a f of a, which they share, and this point, a plus dx, L of a plus dx. What we want to do is we want to know what's the change in y on the tangent line. That is dy, and that is this distance here. And by definition of what we did a moment ago, it's the derivative at a times the differential dx, which we know is also delta x. If I were to use the value on the tangent line to approximate the value on the function, there is error involved. The error is the small difference in y value between those 2 points. We're going to want to know what the error is, and we'll be finding that at the end of this section. Again, the closer that you get to the point they have in common, where you evaluated the derivative, the closer that dy becomes to delta y. This means that as long as dx or delta x is small, then I can approximate the value on the function f of a plus delta x, which is the same as f of a plus dx, with the tangent line approximation, L of a plus dx, which becomes the function value at a plus the derivative at a times the differential dx. If I were to then subtract f of a from both sides of this equation that you see, then I would end up with what you have at the bottom. The difference in the y values on the function are approximately equal to the linear approximation function minus f of a, which I know to be dy, which is f prime of a dx. In other words, what we're saying is delta y is approximately equal to dy, and dy is f prime of a times the differential dx. Again, this only is accurate as long as we are close to the value a, and dx is small. We're going to use this equation that dy is equal to f prime of a dx, and that delta y is approximately equal to dy in order to approximate the actual change in the y value on the function when x goes from a to a plus dx, or a to a plus delta x. Let's take a look now at example 4. In example 4, we have the function y equals x squared plus 2x. We want to find the true change in y values, delta y, and we want to find dy, both at x equals 3, if our delta x or dx is 0.2. To truly find the real change in y values on the function, we need to find the function value at 3 and 3.2. So we need to evaluate the function value at 3.2 minus the function value at 3 to get the actual true value of delta y. Let's substitute those values in now and compute. This would give me 3.2 squared plus 2 times 3.2 minus 3 squared, distribute the negative, minus 2 times 3. When you compute this out, you're going to end up with 10.24 plus 6.4 minus 15, which gives you a true change in the y value of 1.64. Now we want to check the differential dy on the tangent line approximation. We want to see how close it came. In order to do that, you use the equation up here highlighted in yellow. We know that dy is equal to the derivative at that particular point times the change in the x value. Our change is 0.2 and a is 3. So we need to find the derivative at 3 and then multiply it by 0.2. The derivative of my function is 2x plus 2. If I evaluate that at 3, I end up with 6 plus 2, or 8. Then the differential dy, the change in y on the tangent line, becomes 8 times 0.2, or 1.6. As you can see, these are close in value. And again, delta x is small, so I am close to 3. Before we get to calculating error, let's take a look at this particular picture, which demonstrates the last example that we worked. You can see here in blue the graph of the original function, x squared plus 2x. The point we're interested in taking the derivative at is 3, 15, which is up here again in blue. We want to approximate the values, the change in the y values, and we want to compare it to the point 3.2, which on the actual tangent line is up there at 16.64. We have the equation of the tangent line written here in purple. We need to know what's the change and how close these values really are. Looking at the graph, it's almost impossible to tell them apart. The only way we're going to be able to see it is by changing the scale. I need to zero in and zoom in on the region around 3. I know I want to go up to 3.2 or so. So I'm going to go ahead and evaluate between, let's say 0 and 4. Let's see if that pulled them apart enough. No, it did not. We're going to have to go in even more. Let's now try something closer. Instead of going to 0, let's instead start at 2.6. And instead of going up to 5, we'll go up to 3.8. Now can we see? They're still very close together, but if I scroll out, can you see the difference between the two? It's very hard, but if you can remember, the blue is the actual function with the true value at 3.2 of 16.64. The tangent line approximation is below it in purple, with a value on the approximation of 16.6. Again, they're very, very close approximations. Let's now return to our notes and we'll continue with a discussion of the calculation of error. There is error involved. Let's look back at the graph again and talk about what the error is from the graph. The error is the change in y value between the 2 points. Well, that's incredibly small on this one. I had to zoom and zoom and zoom to find it. If you zoom in even more, you could make it exaggerated so you could tell it apart. But notice how close together we are over here on the axis. How do we calculate that error? When we measure things, as we have to do in physics and other applications, there's always error involved. You take a yardstick or some kind of ruler to measure how long something is. There's going to be error. You're not going to be able to get it exactly. We call this measurement error. And if we're measuring a value and an exact value of that measured quantity is A, but we come up with A plus delta X, then we call the delta X the measurement error. There's always going to be error in any kind of measurement. Any calculations done with that measurement will then also have error in it. And this is what's called propagated error. When you do a calculation that involves that delta X, you're going to get more error on the other end. This type of error can be given by delta y equal to the function value at the measured value, A plus delta X, minus the true value, f of A. We are not going to know the true value for the measurement. We can't know it because every time we measure, we have error. Because we won't actually know the true value, we'll have to estimate the true value as well. So we're going to get even more error. What we're going to do is we're going to approximate the exact value of the function with the measured value, which we know has error in it. So if we want to measure delta y, which is approximately dy, change in y in the tangent line, we're going to actually compute the derivative at the measured value, A plus delta x, times dx. It's not right at A where it should be, but we don't know what the true value is. So we're both approximating the measurement error and using an approximation of the true value to do it. We're going to be off. We're typically interested in the size of an error relative to the size or quantity of the thing being measured. We call this relative error. Telling me that you have an error of 5 meters may sound like a lot. That's not much if you're measuring the distance to the moon. Compared to the distance to the moon, 5 meters is nothing. That would be a very accurate estimation. On the other hand, if I'm measuring the length of a room, and I'm off by a meter, that's a lot. It depends on the relationship between the measured value and the thing being measured. What is the relative error? If we have an absolute error, delta Q, for some quantity, the relative error is given by delta Q divided by Q, where Q is the actual true value, the actual distance from here to the moon. But we may not know the true actual distance from here to the moon, so we'll have to approximate it using our measured value. The percentage error is when you take the relative error and multiply by 100. It's just the relative error expressed as a percentage. We want to take a look at this first error example. An astronaut is using a camera to measure the radius of the Earth. He calculates that the radius of the Earth is 4,000 miles, but he knows he has an error of either 80 miles too much or 80 miles too few. That means plus or minus 80 miles. This is his delta X. We're going to use differentials to estimate the relative and percentage error of using the radius measurement that he got of 4,000 miles with an error of plus or minus 80 miles to calculate the volume of Earth. We're also going to have to assume Earth is a perfect sphere, which is not true. It's an oblate spheroid, meaning it's flatter at the poles, but it's going to be an approximation. We're going to be off. We start with the measurement of the radius, the error that we have. Instead of calling it delta x, we can call it delta r or dr, since it is our independent variable. We know it's between negative 80 miles and positive 80 miles. The volume of a sphere is 4/3 pi r cubed. We know from what we did earlier that the change in the approximation function is given by the derivative at that value times the differential dr. What we want to compute then is the differential dv. To find dv, we take the derivative of 4/3 pi r cubed to get 4 pi r squared, and we multiply by the differential dr. This is using that formula that dy is equal to f prime of a times dx. Now that we have this, we can rewrite this formula that we have up here, but with the volume instead. If we use the measured radius of 4,000 miles, we can estimate that the differential dv, the change in the volume, which has to be between negative 4 pi r squared dr and positive 4 pi r squared dr, has to be measured with our approximated value, since we don't have a true value, of 4,000 for the radius, negative 80 dr on the left, and positive 80 dr on the right. If you multiply these numbers out, it looks horrible. This is negative 5,120,000,000 on the left and 5,120,000,000 on the right. The change in our volume is somewhere between those values, which looks ridiculously large. But what is it in relationship to the actual volume of the Earth? Is this a large percentage of the volume, in which case it's not a good approximation, or a small percentage, in which case it is a good approximation? To estimate the relative error, we're going to compute this change in volume that we see here with the volume. We're going to divide dv by v. However, we don't know the exact value for the volume, so we're going to have to estimate it using 4,000, our measured amount, for the true value. This is going to add error, propagated error, into our calculations. This gives us 4/3 pi times 4,000 cubed. If I take this relationship up here and I divide by the volume in each case, what do I end up with? It turns out that if I divide all three parts of the inequality by the estimated true volume, is that even a word, estimated true value? We come up that the change in volume with respect to the true volume is between negative 0.06 and 0.06. In other words, our percentage error is 6%. This is not a huge amount. This is a reasonable approximation. We know that it's actually relatively close in spite of these horrifyingly large numbers here. Let's now take a look at the last example, which is very similar to the one before. Pause the video and work it out, then turn the video back on to compare your answer with mine. Let's now compare our work. We start with the change in the radius being between negative 100 miles and 100 miles. This is the estimated error in measuring the radius. We know that the formula for the volume of a sphere is 4/3 pi r cubed. Using the differential formula, we know that dV is equal to the derivative times the dr differential. This gives us 4 pi r squared times dr. Then we use the dr values that we found up here and the measured radius of 3,950 miles to compute the change in the volume, which is dV. When we multiply it out, we end up with 6,241,000 as the change in the volume. Negative on the left, positive on the right. To find the relative error, what we need to do is divide this by the actual volume. We don't know the actual volume, so instead we use an estimation using the 3,950 miles, which turns out to be 82,173,000,000, etc. When we compute the relative error, we get that the relative error is between positive and negative 0.07595, roughly. The percentage error is then about 7.595%. Why do you suppose it's larger than it was in the previous problem? In the previous problem, our error in measuring the radius was 80 miles. In this problem, the error in measuring the radius is 100 miles. This results in some propagated error. Believe it or not, this is the end of this section. I promised you it would be short, and it is. In the next section, we'll be looking at what we call maxima and minima, the high points and low points on a function. We'll use the derivative to discover where these might occur, which are called critical points. I'll see you in the next video.